All right, so we're going to keep looking at graphical vectors today. And so by now we've done a scale drawing, so we understand what that means. We're going to stop. We're going to take a quick look at some directional information, just so that we have a way to describe these resultants that we're going to solve. And then we'll actually work out a problem or two so you can see those done. So what you should start with in your notes is just a setup like this. And then let's draw a vector in this first area here, quadrant 1. And let's say we had to describe this. So we've got north, south, west, east. And what we have to do when we're talking about directions and with these vectors is we have to be very exact. And so to be very exact, we have to describe not only an angle, which we would measure using a protractor, but we have to measure exactly where that angle is measured from. And we have to describe where that angle is measured from. And so if we have a situation where we're measuring this angle, and we're going to call that theta, just like you guys have seen in all of your math classes. If we're measuring this angle theta, we'd plop protractor down, we'd measure this angle, we get some kind of a number. But we have to be able to describe where that number is measured from. And if you look at this angle, it's coming from the east line, and then you got to go north to get up here to our vector. This arrow represents our vector. And so to describe this angle, what we would say is this angle is some number, let's say 45 degrees, and it's north of the east line. And so we would describe this angle right here as north of east. So I'm going to just write that out. You can abbreviate that NO. E. Notice that we didn't write northeast. Northeast just describes that it's in this area up here, but it doesn't describe where our angle is measured from. So we have to say the of. North of the east line means that it is measured from this line, and we're talking specifically about this angle. Now, if we flip around, we could just as easily have measured this angle right here and called it theta. Still done the same process with protractor. But now, if you notice, this angle is being measured from this line. This is the north line. And to get to our vector, which is here, we have to go east. So this is going to be east of north. So I'll write that in. East of north. And we can abbreviate that EON if you'd like. There's parentheses. So there's that. Again, using the word of because it's showing that it's measuring it from the north line. All right, what happens if we pop over here to the second quadrant and we have this guy and we measure this angle. There's theta. This one's being measured from the west line. To get to our vector, we have to go north. So this is north of west and N-O-W. Could have measured this angle, call that theta. This one's measured from the north line, and we have to go west to hit our vector. So this is west, north. Okay, that takes care of that second quadrant. Down here in quadrant number 3, right here, if we had to measure this angle, call it theta. This is south of the west line. I tried to mess up. I fixed it. There we go. South of the west line. And then if we would have done this angle here, this is being measured from the south line, and we go west. So this is west of south. One last quadrant to go. Very last one here is quadrant 4. Here's our vector. If you do this angle up top, label that. That is going to be south of the east line. And here is going to be east of south. I think you've probably caught on by now. So there is that. Those give us, let's label that, those give us very exact ways to describe where an angle is measured from. And so if a problem gives us north, south, east, west, you want to use one of these 8 descriptors. If the problem doesn't give us north, south, east, west, then you have to come up with a descriptor that still explains where the angle is measured from, which you'll see in a few of the example problems. So That takes care of the direction side of things. We're going to switch over. We're going to look at a couple of the examples from the notes. So I'm just going to switch gears, get some graph paper in here, and the problems. So here we go. Let's say we are looking at, I believe this is the first one from the notes, if you look through the PowerPoint. If we're looking at this problem here, student walks north 50 meters, then walks 40 meters to the east. So you've got two vectors there, you got two displacements. We got to draw these out graphically. And so to do these graphically, the first thing we have to do is come up with a scale. And I'm looking at these, and so our scale is going to involve, show you here, get this graph paper visible. Our scale is going to involve looking at this graph paper and saying a certain displacement is equal to one of these boxes. And so when we look at 50 meters and 40 meters, we want something that's going to fit on this piece of paper, not be too big. But it can't be so small that the lines are tiny, because if you have a really small scale, there's going to be a lot of error. And so you want something in the middle. And so on this one, I think you would either want to do one box equals 10 meters or one box equals 5 meters. Either way would be fine. Both of those scales will work out fine. We're going to do one box equals 10 meters just to keep the math a little bit easier. Not that it would be really that challenging with 5, but we'll do an example of 5 as well. But let's do this as 10. And so let me set this up. First thing to do on graph paper is to write down what your scale is. And so my scale is one box equals 10 meters. So for this drawing, for this diagram, that's going to be the scale. Now, we look at our original problem. Here's our original problem, and we draw our vectors. So 50 meters north. So we need on here an arrow that points north and is equal to 50 meters. And so if you think about it, well, we need 50 meters and each box is 10 meters. That means we're going to need 5 boxes that goes north. So I'm going to draw that. I'm going to, as I draw this on here, I'm using a marker so that it shows up nicely for you guys. I would recommend a very sharp pencil. You want to keep these lines nice and thin. I'm not drawing them thin because you wouldn't be able to see them. So definitely a nice sharp pencil for drawing these. Once you get the first line drawn, it points in the right direction, which is north, and it's 5 boxes, which represents 50 meters in real life. Then it's time for the second vector. The second vector is 40 meters east. And so east is this way. From the notes, there's a section there, there's a slide on there that talks very specifically about something called tip to tail. These arrows, these vectors have to be drawn in order. And so here is the first one. You start the second vector at the end of the first. So here's the end of the first. It has to be drawn up here. You don't want to come back down here to the beginning and draw it. It has to be done from up here at the end of the first vector. And so here is the tip. So the name tip to tail. Here's the tip of the first arrow. It's going to meet up with the tail of the second arrow. That makes sure that we draw these in order the way that we need to. So this one needs to represent 40 meters, which means 4 boxes. So I'm going to carefully draw this. Remember to use a straight edge. There's no freehanding of any kind on these, or there will be lots of error and it won't work out. So from there, if you remember, flash this back on here, that's the end of the problem. Basically, those were the only 2 vectors. If there was a third, you would just draw the third. If there was a fourth, you'd keep going, tip to tail, until you were all the way done. Some of the problems that you encounter will have more than 2, but this one just has 2, so it's basically sketched. And so now what we're ready to do is draw the resultant. We're ready to draw the ending, the final part of this problem. The resultant displacement, if you remember, displacements are only concerned with starting and ending point. And so here was the starting point. These always point towards the end of the problem. So you need to go back to the beginning of the problem to draw the resultant, and it points towards the end. So I'm going to lay the protractor down. I'm going to draw this out very carefully. so that I get something like that. A lot of people like to use a different color here. So if you want to switch over and use a colored pencil or a pen or something like that, or if you just want to, stick with pencil, that's fine too. You don't have to do a different color, but this is your resultant. And so now you've got all the drawing done that you need to. Now we have to apply the scale, because really the problem wants the resultant displacement, which is on this graph, this red line. So first step is to put protractor down and measure this thing out. And do this very carefully and keep as many significant digits as you can without going overboard. That is looking like exactly 3.2 centimeters to me. And I know so out to probably the hundredths place. So that's the measurement that I got just by measuring using the protractor. It should take you, 10 or 15 or 20 seconds to read your protractor, because you got to be exact. So don't just plop it down there and say, oh, it's about 3 centimeters. That's not going to work out for you, so be careful. Once you get that done, now it's time to apply our scale. And so to apply our scale, we're actually going to add one more thing up here. Each of these boxes here is 1/2 of a centimeter. So I'm also going to add this up here, so that we know each of our boxes is the equivalent of a 1/2 centimeter. Now, if you look at the number we just measured, that's in whole centimeters. So we can't directly apply our scale yet, because our measurement does not match up with our scale. And so the first thing to do is basically what we're looking at doing is converting this into 1/2 centimeters. Once we get 1/2 centimeters, we're in boxes, which we know is 10 meters each. And so all we have to do for that step is just multiply this by 2. That'll tell us how many 1/2 centimeters are in 3.2 centimeters. So this is going to be 6.40. And now I could call this boxes, because now all of a sudden we're in 1/2 centimeters, which is the equivalent to a box. And now we can say each of these boxes is 10 meters. And so the last step is just multiplying by 10. We're going to get 64.0 meters as our overall displacement here. So just solved that physics problem, two-dimensional vector physics problem, with just this little drawing from a scale drawing. So here's final answer. Now with this, it's still a vector, so we can't just put 64.0 meters, because we don't know what direction that is. And so we have to measure an angle and describe an angle. And so usually on these drawings, if you can get an angle that's inside the triangle, I would recommend that. Doesn't mean that there aren't other options, but that probably will simplify things down as you get better and better at these. And if you remember using a protractor, which it might have been a while, it really helps to draw, if you have these shorter lines, what I call kind of like a little cheater line up there, just so that that thing will show up on the protractor. And then from there, we can actually plop the protractor down like this and measure our angle. You can kind of get an idea what that's going to be. I'm going to kind of spin around here, make sure everything is lined up. Just scoot that way a little bit. That's pretty good. And then I'm going to read this out. I don't think it's quite 38, but it's really close. I'm going to go like 30, 37.9. So I'm going to call this 37.9 degrees. And then the last thing to do is to describe where we measured that from. That was measured from this line. And if you remember, this is north, and we have to go east to get to our vector. So this is going to be 37.9 degrees east of north. And so I'm going to label that. And so that whole thing becomes your answer. This is all that you need for your final part. So there's a lot to it. You got to be careful. All of these will need directions. All of these will need angles. So don't celebrate once you get to this point. There's still more work to do. All right, I want to do one last problem. This is kind of a harder variety. Same idea, same start. So you're going to look at this and you're going to say, okay, I've got 90 meters horizontal before reaching the first hill, and then it travels up the first hill at a 40-degree angle. So think about what this looks like in real life. Travels horizontal, and then the roller coaster goes up a hill. That's what the generic sketch is going to look like. That 40 degrees, is measured from that horizontal line. So here's the horizontal line. So that's what our scale drawing is going to look like. So try to picture some of these and what they would look like. That way you don't get things pointed in the wrong direction. From here, we can look at our scale. So we can, on this one, I think you got two choices again. I still think you could do 10, like we did on the last one, or you could do 5. And so I think maybe it's a good idea to try one with 5. It's going to be a little bit of a bigger drawing, but I think we can handle it. So that's kind of the generic setup. I'm going to switch back over to the graph paper. Because I'm switching drawings, I'm switching scales, I've got to relabel this. So one box now is going to equal 5 meters. And we now know that that's a ½ centimeter on this graph paper as well. The first one was 90 meters horizontally. So 90 meters, if 5 meters for each box, we're going to need 18 boxes. So I'm going to plop down here and I'm going to sketch this out. 18 boxes again, straight edge, nice and straight lines. And I'm going to double check, 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep, got 18 boxes. Okay, so we got it. Second line on this one is harder. Second line is harder because it is at an angle. Because it's at an angle, if you can kind of imagine this, it cuts through parts of boxes. So on this one, we can't count boxes because the next number is 50 meters. So we can't say, oh, 50 meters, we need 10 boxes. Plop down here and try to draw this at a 40-degree angle through 10 boxes because we're not going to go through complete boxes. So we have to do a little bit of math. The first thing I would suggest, though, is let's get this set up. Throw your protractor on there right at the end of that first vector where we're going to draw the second. Get everything nicely aligned and put a little dot at 40. So there's my dot. I know that this has to be drawn at a 40-degree angle, and I now know that if I draw it like this, there's your 40 degrees. You can't, you got to draw it at exactly that 40-degree or it's not going to work out. So that's what our little dot there is for. The tricky part here, we got to figure out how long to make our line. We know in real life, I'm just going to come over here and solve this out. We know in real life that this needs to represent 50 meters. To figure out the length of a line, we basically kind of do the exact opposite of what we did up here. Okay, so we multiplied by 2 and by our scale. Here what we're going to do is the exact opposite. So we're going to divide this by our scale, which is 5. So we're going to come up with 10. And then we're going to divide this by 2 again to get whole centimeters because this is in boxes. So we need 10 boxes, but we can't just count boxes. But if we divide this by 2 again, we'll get whole centimeters, which then we can measure out. So this is going to be, as you can probably see, 5 centimeters. So this line needs to be drawn exactly 5 centimeters in length at this 40-degree angle. So exact opposite of what we did up above. Divide by scale, and then divide it by 2 to get it in whole centimeters, instead of up here, multiplying it by 2 to get it into ½ centimeters, and then multiplying by the scale. All right. These steps will always be the same. So I know that's probably the most confusing part, is understanding why you multiply by 2. So practice it, but if worst comes to worst, just memorize that you have to multiply all the time, every single time if you're solving a result, but you have to multiply it by 2 and your scale. If you're figuring out length of a line that's at an angle, or not at an angle for that matter, you're going to divide by the scale and divide by 2. So we're looking at 5 centimeters here. I'm going to get this lined up, which is going to take a second. Remember, you want everything to be perfect, right on that angle, exact length. Okay. So there's our roller coaster. We did it. That's the sketch. Time for the resultant. I'm going to switch colors here, put a nice green line on there. So here's the whole roller coaster. Resultant, remember, gets drawn from the beginning, which is here, and connects to the end here. It points that direction. So protractor, still long enough to reach. If you get too big of a scale, you might have to switch over to a ruler. This one still worked out, but much longer, and the protractor wouldn't have worked, so you could possibly need a ruler. All right, there's the resultant. Next step, measure the resultant, and remember to do that very carefully. All right, let's see. Looks a little bit under 13.2. I'm going to call it like 13.18. 13.18 centimeters. That's the length. And so now remember, we're going to multiply that by 2 to get that to half centimeters. We did that right. So that is now in boxes. Each box represents 5 meters in real life. So we're going to have to pull out the calculator for that one. So that line, that total displacement of the roller coaster, 131.8 meters. We still need to do the angle, so just like before, go back to the original starting point. And if you can, stay inside the triangle, so that angle right there is the one that we want. Nice big drawing. We're not going to need any cheater lines on this one. Get everything aligned. Then measure. We're looking at a little above 14. We're going to call it about 14.3, I think. And you notice on this one, there's no mention of north, south, east, west, so we can't say anything about that in our description because we don't know what way this is pointed in a three-dimensional world. And so we got to describe it the best we can. The best we know is that this is the horizontal. This is the ground. And that angle is measured above that. So I'm going to call this above the horizontal, but you could do above the ground as well. Both of those are pretty good descriptors. So I'm going to call this above horizontal. And then that one's done. Now the grading for these, and I didn't do it up top, which maybe we can go back up and do that. But down here, I'm basically going to give you a cushion because we're all going to have different drawings, and there's got to be a little bit of error that we're going to allow, even though you're going to actually be surprised like how accurate you'll be. I'm going to give you a 3% cushion above and below the values here. So when I go to grade this, I wouldn't expect you to have exactly 131.8. But you got to be close. And so let me just see what 3% of this is. You're looking at about 4 meters. So the range for this is going to be somewhere between 127.8 all the way up to 135.8. And so I would look at those answers as all being 100% correct. From there, if you're off, is it small or is it a big goof? That's going to kind of dictate how many points you would miss. We'll do the same thing with that angle. We have 14.3. We're going to do plus or minus 3% on that, which is about a ½ degree. So you could be as low as 13.8, and you could go up to 14.8 degrees. So there's your range. This one would be scaled the same way. I guess we could do that really quickly because you'll want to probably check your answer. That's about 2. So you're looking at a range between 62 and 66 meters on that. And 37.9, 3%, about 1.1. So you could go as low as 36.8 and as high as 39. So there are your ranges to get full credit. So see where you're at. Hopefully that turned out okay. I don't think any of the ones that you'll encounter will be any more difficult than one of these two. So hopefully that helps.